When measuring voltages on a 277/480 volt panel, you can expect specific readings between lines and ground, as well as between the phases themselves. Firstly, let's consider the line to ground voltages. When placing a voltmeter between line 1 and ground, you should measure approximately 277 volts. Similarly, when measuring from line 2 to ground, you should also read around 277 volts. And lastly, when measuring from line 3 to ground, you should again find a voltage of approximately 277 volts. These readings are characteristic of a 277/480 volt Y-connected system. Now, let's examine the phase-to-phase voltages. This involves measuring the voltage between any two lines. When placing the voltmeter between line 1 and line 2, you should measure approximately 480 volts. Likewise, the voltage between line 2 and line 3 should also be around 480 volts. Finally, measuring between line 1 and line 3 will also yield a voltage of approximately 480 volts. These phase-to-phase voltages are also typical for a 277/480 volt system. It's important to understand that in a 277/480 volt system, it is not possible to directly obtain 120 volts from any of the lines without the use of a transformer. This is because the voltage difference between any two phases is 480 volts. Obtaining 120 volts would require stepping down the voltage. This is commonly achieved using a transformer. A transformer is an electrical device that transfers electrical energy between two or more circuits through electromagnetic induction. A step-down transformer reduces voltage from a higher level to a lower level, such as from 480 volts to 120 volts. A transformer consists of two or more coils of wire, electrically isolated but magnetically linked. A varying voltage in one coil creates a varying magnetic flux, which in turn induces a voltage in the other coil. The ratio of the number of turns in each coil determines the voltage transformation ratio. For example, to step down 480 volts to 120 volts, a transformer with a turns ratio of 4:1 would be required. This means the primary coil, connected to the 480 volt source, would have 4 times as many turns as the secondary coil, which provides the 120 volt output. Transformers are widely used in electrical systems to adapt voltage levels to suit different applications. They are essential for distributing power efficiently over long distances and for providing the appropriate voltage for various types of equipment. In the context of a 277/480 volt system, a transformer would be necessary to supply 120 volts for lighting receptacles or other low voltage devices. Without a transformer, directly tapping into the 277/480 volt lines would result in excessive voltage, which could damage or destroy equipment designed for 120 volt operation, or create a safety hazard. In summary, a 277/480 volt panel provides 277 volts from each line to ground and 480 volts between any two lines. To obtain 120 volts, a step-down transformer is required to reduce the voltage to the desired level. Now let's delve a bit deeper into three-phase systems and why these specific voltage levels are common. A three-phase power system is a method of alternating current power generation, transmission, and distribution. It is the most common way that electric grids worldwide transmit power. Three-phase systems are more efficient than single-phase systems because they deliver power more evenly, reducing voltage fluctuations and requiring smaller conductors for the same power transfer. A 277/480 volt system is a common configuration for three-phase power distribution in commercial and industrial buildings. The 480 volt refers to the phase-to-phase voltage, while the 277 volt refers to the phase-to-neutral voltage, which is also the phase-to-ground voltage in a grounded system. The relationship between these voltages is determined by the square root of 3, approximately 1.732. Specifically, 480 volts divided by the square root of 3 equals approximately 277 volts. This mathematical relationship is a key characteristic of three-phase Y-connected systems. The Y connection is one of two common configurations for three-phase systems. The other is the delta connection. In a Y-connected system, the three phases are connected to a common neutral point, forming a Y shape. The neutral point is typically grounded, providing a reference point for voltage measurements and a path for fault current to flow back to the source. In a delta-connected system, the three phases are connected in a closed loop, forming a triangle or delta shape. Delta systems do not have a neutral point, and the phase-to-phase voltage is equal to the phase voltage. Understanding the difference between Y and delta connections is crucial for working with three-phase power systems. In a 277/480 volt Y system, the 277 volt phase-to-ground voltage is often used for lighting circuits, while the 480 volt phase-to-phase voltage is used for powering larger equipment such as motors and HVAC systems. Using 277 volts for lighting can reduce the current required for each circuit, allowing for smaller conductors and lower installation costs. However, it's important to use lighting fixtures and ballasts that are specifically designed for 277 volt operation. In addition to voltage measurements, it's also important to consider other electrical parameters such as current, power, and power factor when working with three-phase systems. Current is the flow of electrical charge, measured in amps. Power is the rate at which electrical energy is transferred, measured in watts or kilowatts. Power factor is a measure of how effectively electrical power is being used, with a power factor of 1 indicating perfect efficiency. These parameters are related by the following equations: power equals voltage times current times the power factor. And in a three-phase system, the power calculation also involves the square root of 3. Proper measurement and calculation of these parameters are essential for ensuring the safe and efficient operation of electrical equipment. When troubleshooting electrical problems in a three-phase system, it's important to use appropriate test equipment and follow safe work practices. A multimeter is a versatile tool that can be used to measure voltage, current, and resistance. A clamp on ammeter can be used to measure current without interrupting the circuit. An insulation resistance tester, also known as a megameter, can be used to test the integrity of insulation. Before working on any electrical equipment, it's essential to energize the circuit and verify that it is indeed dead using a voltage tester. Lockout-tagout procedures should be followed to prevent accidental re-energization. Personal protective equipment, such as insulated gloves and safety glasses, should be worn to protect against electrical shock and arc flash hazards. Remember, electrical work can be dangerous, and it's important to be properly trained and qualified before working on any electrical system. If you are not comfortable working with electricity, it's best to call a qualified electrician. Also be aware of NEC Article 210.6, which provides guidance on maximum voltage limits for branch circuits, and NEC Article 480.4, which relates to the overcurrent protection of the system. Keep in mind, these articles should be read in their entirety to fully understand the requirements. When dealing with three-phase power systems, the grounding is a critical aspect for safety and proper operation. Grounding ensures that metallic enclosures and non-current carrying parts of equipment are at ground potential, minimizing the risk of electric shock. In a 277/480 volt Y-connected system, the neutral point is typically grounded, providing a low impedance path for fault current to flow back to the source. This allows overcurrent protection devices, such as circuit breakers and fuses, to quickly interrupt the circuit in the event of a ground fault. The grounding system must be properly installed and maintained to ensure its effectiveness. This includes using appropriately sized grounding conductors, making proper connections, and regularly inspecting the system for any signs of damage or corrosion. The National Electrical Code, NEC, provides detailed requirements for grounding electrical systems. Article 250 of the NEC covers grounding and bonding, and it's essential to follow these requirements to ensure a safe and compliant installation. Also, the size of the grounding conductor is crucial for safely handling fault currents. NEC Table 250.122 provides guidance on the minimum size of equipment grounding conductors for various circuit sizes. It is critical to use the correct size to ensure proper fault current flow. In addition to grounding, bonding is another important aspect of electrical safety. Bonding involves connecting metallic parts of the electrical system together to create a common electrical potential. This helps to minimize voltage differences between different parts of the system, reducing the risk of electric shock. Bonding is typically achieved using bonding jumpers, which are short lengths of wire that connect metallic enclosures, raceways, and other non-current carrying parts of the system. The NEC also provides requirements for bonding, including the size and installation of bonding jumpers. In summary, grounding and bonding are essential for electrical safety, and it's crucial to follow the requirements of the NEC to ensure a safe and compliant installation. It's also vital to have a good understanding of overcurrent protection. Overcurrent protection devices such as circuit breakers and fuses are designed to protect electrical circuits from excessive current, which can cause overheating, damage to equipment, and even fire. Circuit breakers are automatic switches that interrupt the circuit when an overcurrent condition is detected. Fuses are one-time devices that melt and break the circuit when an overcurrent condition occurs. The size and type of overcurrent protection device must be carefully selected to match the characteristics of the circuit it is protecting. The NEC provides guidance on the selection and installation of overcurrent protection devices. Article 240 of the NEC covers overcurrent protection, and it's essential to follow these requirements to ensure proper protection. The interrupting rating of the overcurrent device is also an important consideration. The interrupting rating is the maximum amount of fault current that the device can safely interrupt. The interrupting rating must be greater than the available fault current at the point of installation. If the interrupting rating is too low, the device may fail to interrupt the fault current, which can result in a dangerous arc flash. Short circuit current ratings, SCCR, are also important, especially with industrial control panels. Furthermore, coordination of overcurrent protection devices is essential to ensure that the device closest to the fault interrupts the circuit, minimizing the impact on the rest of the system. Coordination studies are often performed to determine the optimal settings for overcurrent protection devices. In conclusion, overcurrent protection is a critical aspect of electrical safety, and it's essential to follow the requirements of the NEC to ensure proper protection and coordination. Now let's talk about harmonics and three-phase systems. Harmonics are distortions of the sinusoidal waveform of alternating current. They are caused by nonlinear loads, such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can cause a variety of problems in electrical systems, including overheating of conductors and transformers, increased energy losses, and malfunctioning of equipment. To mitigate the effects of harmonics, various techniques can be used, such as harmonic filters, line reactors, and power factor correction capacitors. Harmonic filters are designed to block or reduce the flow of harmonic currents. Line reactors are inductors that are placed in series with the load to reduce harmonic distortion. Power factor correction capacitors can help to improve the power factor and reduce harmonic distortion. The NEC also provides guidance on dealing with harmonics. Section 220.61 addresses the sizing of neutral conductors in systems with harmonic currents. It's important to properly size the neutral conductor to handle the increased current due to harmonics. In addition to harmonics, voltage imbalance can also be a problem in three-phase systems. Voltage imbalance occurs when the voltages in the three phases are not equal. Voltage imbalance can be caused by uneven loading, unbalanced impedances, or problems with the power source. Voltage imbalance can cause a variety of problems, including overheating of motors, reduced motor life, and increased energy losses. To mitigate the effects of voltage imbalance, various techniques can be used, such as balancing the load, correcting the impedance, or improving the power source. Voltage imbalance can be measured using a voltage meter or a power quality analyzer. The NEC does not specifically address voltage imbalance, but it's important to be aware of this issue and take steps to mitigate its effects. So, to summarize, dealing with harmonics and voltage imbalance are crucial, and various techniques can be employed to mitigate their effects. Furthermore, understanding motor control in three-phase systems is essential. Motors are common load in three-phase systems, and they are used to power a wide variety of equipment. Motor control involves starting, stopping, and controlling the speed and torque of motors. There are various types of motor starters, including across-the-line starters, reduced-voltage starters, and variable frequency drives. Across-the-line starters apply full voltage to the motor terminals, resulting in high starting current. Reduced-voltage starters reduce the voltage applied to the motor terminals during starting, reducing the starting current. Variable frequency drives, volts per hertz, allow for precise control of motor speed and torque by varying the frequency and voltage applied to the motor. The selection of the appropriate motor starter depends on the application and the size of the motor. The NEC provides guidance on motor control and protection. Article 430 of the NEC covers motors, motor circuits, and controllers, and it's essential to follow these requirements to ensure proper operation and protection. Motor protection is also an important consideration. Motors must be protected against overloads, short circuits, and other faults. Overload protection is typically provided by overload relays, which are thermal or electronic devices that trip the motor starter when an overload condition is detected. Short circuit protection is typically provided by fuses or circuit breakers. In conclusion, motor control and protection are essential for the safe and efficient operation of motors in three-phase systems, and it's crucial to follow the requirements of the NEC to ensure proper operation and protection.